Welcome to InstaSpool Performance, Savage Fabrication. I am Bradley Carter, owner-operator. Behind the camera is Dalton Carter, my brother. He does all the editing and puts all the parts together for everybody. So our hands are what assemble your parts. There's nobody else here, just us. So all the crazy ideas and modifications and everything we do, all done here by us too. So we kind of left off last time about talking about how to tune using what's coming out of your exhaust pipe. Because it's diesel fuel, we create soot. That just so happens to be part of the diesel chain, the way it burns and mixes. We get acetylene formations, and if we don't burn off those acetylene formations, we see soot particulate out of the exhaust. A question that seems to come up still, even though we don't have the video up yet, is I put on all these new parts at once and the truck is super smoky. Do I need more turbocharger? No. You have failed to tune to all your new components to answer that. We can kind of go over what we did last time a little bit, and then we can kind of get into some new stuff. But the bane of diesel itself is the fuel type. We've talked about AFRs quite a bit. Diesel has an AFR that's infinitely high. Essentially, it'll go up and run an AFR as high as we can get it to. There's a point where the power production is either so low because we pulled fuel out to make AFR go up that the piston won't accelerate, ain't producing torque. And then there's the other spectrum where to make the AFR go up, we have ran out of turbocharger. Or we should say, compressor capacity. Say like a system that may need 700 pounds a minute to run 35 to 1 AFR. The turbocharger to do that is going to be absolutely huge and will not fit inside of a over-the-road light-duty diesel truck. So stuff gets really, really big and then just kind of stops working. So what we have here from last time is our chart of our RPMs using the 359 cubic inch engine or a 5.9 liter Cummins, all 80% VE, keep it easy. And these are the NA CFMs. So we know that all a turbocharger does, it doesn't do any magic, no fancy sauce. All turbocharger does is multiply what the engine's consuming normally aspirated. That's all it does. Doesn't do anything more, doesn't do anything less. There, you can argue in really technical form that there are a few things that happen when we increase the pressure in the system as well as the pressure in the combustion chamber. We could do those on a different video. They might be towards the end of this video. We'll see if we get there or not. So we know that all turbo does is multiply the air density. So we know that with this size engine, this is all we get, no matter what, unless we rev the engine up higher. That's why making the cubic inches bigger, like going to a 6.6 Duramax or a 6.7 Cummins, or even for, say, a 6.7 Power Stroke or a 7.3 Power Stroke, where the cubic inches is higher, that NACFM gets higher, and it takes less boost pressure to net the same pounds minute consumed. That's why we see bigger engines spool the same size turbocharger faster. So I hope that kind of ties up some of the questions that we've gotten lately. I guess we'll go real quick. When we make a turbocharger bigger, it always spools slower. There's no way around it. Physics says that when the surface area of what we're trying to drive gets greater, it's going to take more energy to drive that same amount of surface area a revolution in the case of a turbocharger. So when they get bigger, we have more parasitic loss in the system, and because we're driving the compressor wheel with the turbo wheel, which is then extracting energy from a compressible gas being the exhaust, we get lag as well as some reluctance from when the pressure in the system comes up versus when the turbine actually reacts to the increase of energy in the system. It'll compress kind of like a rubber band or a spring wheel before it actually reacts, and you could watch this on a gauge when that happens. So when the turbocharger gets bigger, it spools slower, so we actually need to put less fuel in at these lower RPMs when the charger is coming online. So at these lower RPMs, we might only have, where before we had 10 pounds of boost, and now we only got 5 pounds of boost, we have to actually put less fuel in to maintain AFR that's appropriate for what's coming out of the exhaust until the turbo gets up to a boost pressure that's above the factory rating or above what it was previously, typically, before we can put more than fuel in than we did previously to maintain the proper AFR, or at least keep the smoke down to a haze. And at that point, once we go above the OEM boost level, or we rev the engine above where we were last time, we'll see a power gain. A real common thing that I kind of see online a lot of times, this is towards like the ported heads and stuff, is a lot of people that port heads will be, or will say, before we ported the head, it took 80 pounds of boost to make 800 horsepower. And now with the head ported, it takes 40 pounds of boost to make the same horsepower. What they left out of what they're telling you is that after they ported the head, they rev the engine twice as high. Yeah, so there's things that are not put into context to help sell a product, and we want to be mindful of those things, because if we do the math, we know that we would not be able to attain the same 800 horsepower with the 40 pounds of boost if we know it took 80 pounds before, unless some very extreme things occurred. Seeing as we're still on the same diesel fuel, it would have to be in the charge cooling system, and the engine would have to become overly volumetric efficient, which we don't typically see in turbocharged engines. We normally will not see above 100% VE on a turbocharged, especially at least turbo diesel that runs really high boost pressures. The VE tends to not get up to that. Yeah, so hope that kind of all makes sense. And we're going to get into our next thing. All right, so we're going to move into understanding the injection event. What is it? And maybe we'll get into why it's so important. This is another long-winded one, but the injection event is, besides having enough air in the system, the most critical part. Is why we like to see quality injectors on things. And when we have high EGTs with a turbocharger and intercooling system that we know works well to a certain RPM, we've repetitively tested it not only on our dyno and in competition, but others have as well. And we get the results back from them. But we get the one setup that someone's having trouble with, we can verify that the charger is not the issue, the engine size is not the issue, because we have all the data to back this up. Typically, it comes back around to be there is something up with the injector. They're either cheap injectors, second-hand injectors, third-hand injectors. All those things play a big factor. So what we're looking at with the injection event is all injection events have a curve to them. So we're going to be flat. And we're going to come up the curve. We'll maintain a pressure. And then we will come down the curve. So there's the ramp up, the spray duration, and the ramp down. How this looks in different systems is we can look at a mechanical system, and the mechanical system has to ride up a cam plate or a cam. So on VEs and VPs, this is going to be a cam plate. This cam plate has a profile to it that is typically from the OEM is going to be a ramp rate profile that's reliable for the long duration, so they're not repairing pumps. It's no different than if you're a spark ignition guy, camshafts. And the top camshafts, how aggressive can you get with the cam? Well, you get as aggressive as your lift system and valve spring system can handle. Kind of the same thing with mechanical setups on these rotary pumps with the cam system. So as the plunger system rides up the cam, we build pressure until injector opens. Injector is going to actually open somewhere in this rise. Just because the injector is open doesn't mean that it holds what the injector's pressure is. It's just set to open at this point, and then the cam system will continue to increase the pressure in the system, and then it'll hold on to it. Now, on a VE and a VP, their profile is going to not really have a flat top to it. I would say it's going to be more like this. There's not enough room in those pumps to have this kind of position. You might see a plateau if the pressure is balanced. So say the injector gets popped open and the pressure begins to rise, but there's a point where the injector is flowing enough versus how much pressure can be made, you would see this flat point. This is a lot of stuff that is not online, is not in videos, and is very rarely talked about, and is yet so important. A P7100 runs a cam inside of its injection pump with lift profiles, and it looks just like the camshaft in the engine itself or any other engine for the most part. We have found some weird looking ones that seem to have a lobe on the cam that seems to go up and then hold on to this profile, so it would be a ramp up. And then they stay high for a while and then ramp down. I don't really understand what that is for. If you look at any of the aftermarket cams, and I think some of the OEM cams, they have a more standard, like this would be a circle, and it would come up and it holds it. I don't know why you'd want to leave that up there and not drop it down and fill the plunger. Haven't found anything online about that. Just saying that there are some that are shaped like that, in case anybody wants to say there's anything different. All your aftermarket ones for P700, as well as I think some OEMs, I think it's okay to say, they're hard to find stuff, but most of them have a normal looking cam profile, and they're going to have a different rate. I should draw that better. They're going to have a different rate on the lift side and the drop side. So I'm going to come up and say taper off, like so. And what this is doing is it's lifting a plunger inside of a bore. It looks just like a cylinder. So it just looks just like a cylinder and a piston, but instead of a crankshaft, there's a cam right there. And there's a roller lifter on the bottom of the plunger. And it rides up that cam lobe. And there are spill ports inside. So if you were to kind of take a side view look at a plunger, everything around the barrel is full of fuel. There's 2 spill ports. And as long as the plunger is below, the spill ports will fill. And then once this comes up, the top of the plunger will cap off the 2 holes. And now all the fuel in here begins to increase in pressure because it has to, because everything's connected together mechanically. And it's going to begin the injection event as soon as the pressure is enough to open the pop pressure on the injector. And then it'll continue to rise in pressure, but maintain the injection event until there's basically machined ports on the side of here that once they raise up high enough, they will uncover the spill, these are called the spills, and all the pressure will bleed back into the case. But that doesn't mean that the injector line just dumps all its pressure instantly. There's still a blowdown phase, as we can kind of call it based on like an exhaust phase or a pressure reduction phase. There's a blowdown phase where the pressure in the system is reducing, so the spray plume is reducing in pressure but still spraying. So that's really important to know. On common rails and H-pops for the Ford guys, common rails for Duramax, Cummins, and then your newer Fords, they work the exact same as a fuel-injected injector, where they have a coil. Is probably not at all how it looks, but they have a coil above the injector. Just as the button, it's actually like a lift valve. This is connected to the seat, called a pintle. And what they do is when you energize the coil, it's going to pick the seat up. And when we de-energize the coil, it's going to put the pintle back down. Now, we might just think that it's instantaneous into the human brain, it is instantaneous. I don't think there's any possible way for us to see it without a really fast camera. If you looked at the way the coil is energized and then de-energized, it is shaped exactly the same. There's an amount of time it takes to energize the coil. You can see that there's a duration here. There's an amount of time it takes to energize the coil as well as lift the pintle. So the injector doesn't have instantaneous full flow as soon as you command it to open. There's a delay in when it has full flow. And then at the same time, there's a delay when the injector continues to flow while the pintle is coming down. So it's reducing inflow this amount of time, and then it also takes this amount of time to achieve peak flow. Now this all happens extremely fast, but to the engine, it cares about all of this. Why, when the injector gets bigger, the duration automatically gets shorter for the same quantity. You got a lift pintle. HPOP, same thing. You guys open your injectors electronically with a solenoid. You just have oil pressure doing the opening and closing. Pretty sure that's correct. You have the oil pressure opens and closes the solenoid, and you open a valve electronically to actuate that. And you still have high pressure fuel. High pressure. I don't see that right, how you push fuel in the oil. I think the oil is actuating the system. If I am wrong, tell me. I'll correct it next year. So you have a lift pintle. This lift pintle seats, they seat in different places based on the injector design. But for the case of drawing this, pintle seats here. And there are holes here. As the system gets larger, or say the hole size gets bigger, you can look at a couple different things. Per amount of lift of the pintle off the seat, if it's larger, this space gets bigger, faster per millimeter of lift up. That's how you run into where the hole size here can get really large, and you'll actually not have enough space to flow fuel around the pintle into the hole, in which you get a low, you're like limited the injector to get bigger, but the pressure just drops coming out of the nozzle. That's when people talk about dual feeds and triple feeds. What that is, real quick, maybe some people are curious about this that have no idea. It's not feeding multiple injector lines to an injector. The injector line comes in through here, and inside of this system, the fuel actually gets kind of sent off to one side or the other. If you were to separate these from each other as it comes down, on a single feed, or most of your OEM injectors, there's a single feed port that comes down and feeds the nozzle. What eventually happens is the amount of fuel that we're flowing out of the tip is starting to exceed what the body can flow. So when we talk about multi-feed holes, we're talking about adding more feed holes in the body itself to the same one nozzle. So it's still one injector line, which is flowing an adequate amount, and it's still one nozzle that's flowing an adequate amount. But a dual feed or triple feed injector has an extra feed hole to the nozzle, or 2 extra feed holes to the nozzle for triple feed. It's something I actually didn't know for a long time. I had no idea. People say they have dual feed injectors or triple feed injectors, but yet there's only one injector line going to them, and it's really confusing. It's all internal. You can't even see it. But sometimes you'll see people post up a photo of a body with the top off of it, and it's the lower body half that you'll be looking at that'll have these holes around the outside of it. Some of those are lubrication feed holes or feed hole, and the other one is a feed hole to the nozzle itself. So when they talk about dual feed, triple feed, that means your injector builder took your body and put more feed holes in it.
So you put a big injector in, now you don't have enough pressure.
You know what happens with that?
Yeah.
Peak horsepower goes down. It'll make more power. So if you put a really big injector in, and the system has the pumping mechanism is inadequate in its ability to maintain pressure over our injection event. So like watch this. So here's injection event. However you want to draw. We can draw like this. This is our like peak duration, and then you would measure the full duration from opening to closing. Full dur. What happens, we've done this on the dyno, and we have all the dyno graphs to back it up. We've done it with a VP power truck. Now we know that VP pumps, they get a lot of trash talk, basically because way long ago, people were modifying them without putting fuel pressure gauges on them, and they would run the things out of fuel pressure. And fuel pressure is not what killed them, it's fuel volume to keep them cool. And you know that you have volume through the system if you have pressure with an appropriately sized line. So we know they have a limitation. What we'll see is when we put too big of an injector in. So we know the pump's the same. We change out the injector, change out the injectors, change out the injectors. What we will see is the fuel quantity will go up. So let's say we drew this. So torque goes up. Torque and horsepower will go up at lower RPMs. As long as there's enough turbocharger and the turbo's aligned, power goes up. So the fuel quantity's gone up, but peak will go down. All of a sudden, the injector closes early. And it looks just like that. It looks kind of like that, but more abrupt, because what's happening is as the engine RPM goes up, the pump's trying to move more and more cc's through that injector in a shorter amount of time. So the refill rate, or the ability for the system to refill, becomes inadequate, and it can't maintain pressure in the line for the full duration of the event because there was not enough time to refill its spill port or its fuel galley inside the injection pump. So we will make more power with an injector that gives us proper duration, more peak. It'll make a higher peak number, horsepower and torque, but we typically will see it make a little bit less power through the mid-range up to the point that we run out. So we'll put a bigger injector in, and we made, say, on this run, say we did 600 horsepower at 3,000 RPMs, and this one did 700 horsepower at 3,000 RPMs. But this injector also did 900 horsepower at 3,700 RPMs, and this thing topped out at 743 at it didn't go, it just goes up, and then you'll see the power just goes like this. It would top out at, say, 740 or 720, whatever you want to say, at 3,200 RPMs. And that's because we have ran out of the injection pump's ability to maintain a full injection event in the system. And how to bring this across different platforms is in a common rail. What you guys say is that I'm losing line pressure. I can maintain line pressure up to 3,000 RPMs, and from 3,000 to 3,300 RPMs, I'm losing line pressure, and we'll notice that horsepower starts to fall with it, versus a system that can maintain the line pressure at 3,300 and 3,400 RPMs. Tricks that you guys do to get around this is you can run a bigger injector for the CP3 that it's being used. So you can run less duration, but still put the same quantity in, and that gives the rail more refill time between injection events. That tends to let you guys take it out to a higher RPM. On P700s, it's the same as a VP and VE. A VP is mechanically injected, electronically controlled, per se, to a degree. VE, but they all have plungers. So a VP pump has 3 plungers in a triangle. It has an OD style cam plate that it rides around with the 3 plungers riding up lift lobes at one time per injection event. So it's still mechanic. The pressure in the pump is made mechanically. So VE, VP, P700s, all mechanical things. The other thing to consider too is we talk CCs a lot, but we never talk at what RPM are we making those CCs. So we talk about refill times, stuff like that. So they never talk about like what RPM it's making those CCs. So like on a VE pump, say we bought a VE pump and it flows 270 cc's. It does not flow 270 cc's at idle. It also doesn't flow 270 cc's at 4,000 RPMs. It has a fuel rate curve. And VEs kind of tend to do this. They start off actually pretty decent, and then they will come up, and then they'll hit an RPM where they can't, their refill time, and the plunger system gets too short, and they do this. So the RPM is going up, but the CC rate is going down, even though the governor, say we put 3,200 gov springs in it, and this is 3,200, we still have less fuel here than we did at 2,600 RPMs. And that's by nature of the beast. That's how the injection pump functions. We have CC graphs for VE pumps that can show this. P700s do the same thing, but they do it a little bit differently. A P700, it typically actually tends to get up to a CC and then it just maxes at that CC. So as the RPM comes up, the CCs will come up with it available. So it's like a capacity, just how we talked about turbochargers have to have a capacity. Injection pumps also have their own capacity. So we can be, I'm going to draw this out real quick, but a P700 tends to do this. Let me just go flat. So this might be, so idle, this might be 3,000. And then this is 4,000. It just holds this flat line. It doesn't go up, and this might be 2,000. But how is it a capacitive device? We can do that real quick. So as the system revs the higher RPMs, we're turning that mechanical injection pump, which is a pump, over at a higher rate of speed per minute, meaning that the cc's minute goes up, and it goes up to a point where the system will flatline you. So say I have to turn the engine 3,000 RPMs to get my particular injection pump to move 400 cc's. And then at 2,000 RPMs, I'm at, I know it's not linear, but we're just going to do this. It's going to get me in trouble. Just say it's 200 cc's here. But let's say that we're cruising at 2,000 RPMs at 70 miles an hour, 60 miles an hour if we got 410s. You may only be using 70 cc's. And this we can go back to where we're talking about the spill ports are getting opened earlier based on where the plunger has been rotated inside of the barrel. So we only need to put in this many cc's. But if I were to floor it and I had full rack available, so my AFC foot was all the way forward, I can floor it instantly to 200 cc's. And now because we're a turbocharged system, that would cause a lot of black smoke. Because the turbo is probably at 5-10 pounds of boost, and our AFR is not correct to burn the 200 cc's at that window. So we typically roll it, and while we're rolling, RPM comes up, and then we're at 300 cc's, and it's a domino effect. Stuff gets crazy, go real fast. So just like turbochargers have capacities, so do injection pumps. So that's important to note too, is where is your max CCs at? And that P pumps, just because you rev them, don't flow more CCs if the system is designed to be capped out at that amount of CCs. So on a common rails, you could make them look like that. You can make them look like that. You can make them look like that. Because, I mean, RPM does help quite a bit because you're driving you're feeling the rail. But because you guys run so much pressure, I'm pretty confident if you asked the tuner that if you switched it to tune 5, the truck turned off because it overfueled, you could do that pretty easily just because you have this rail full of 30,000 PSI and just the injectors are barely opening. But if you wanted to tell the computer to hold them open for a long time and put a large quantity in all at once, you could probably be really bad. That's probably how that lope tune stuff was getting done early on. That went way fast. But it's still the same with the CP3. They like, the more you look at it from like a rail pressure standpoint, is I might have a really big injector with a a single CP3, and if I tried to command 2,000 US at 3,000 RPMs, it dumps the rail pressure. But if I wait until I'm at 3,000 RPMs, let's just say we went 1,000 RPMs higher than last time and then commanded 2,000 US, there's a good chance that the rail pressure would be okay. I'm not a common rail guru. I could totally be wrong on that, but it is a mechanically driven lift pump, high pressure lift pump to the rail. And if you turn it faster, it should deliver more CCs. So you'd have this thing where you're just kind of looking at, do I need more CP3 at these lower engine speeds to maintain the rail pressure in it? The other thing, we're just going all kinds of just knowledge bombs right now. The other thing is injection pressure. It's really, like, injection pressure is super, super critical. The harder you push on the backside of a stream of liquid, the more you're going to fit through a hole. Liquids don't tend to have to follow our sonic limitations like air does. So that's why you see cone rails lose a ton of power when they drop rail pressure, and that's because, one, the fuel quantity is reducing quite a bit, as well as the atomization that those injectors are designed to run based on the nozzle configuration is starting to go off design. So that's why we see, like, in the performance stuff and sled pulling, when it comes to the P pumps, we'll often raise the pop pressure of the injector itself to increase the amount of maintained pressure in the line for the injection event, because even though it seems weird, all we do is just put more timing in it. The timing's still back where it was, but we raised the pop pressure. That would retard our timing, so we just advance it in the pump to put it back where we want it. What that does is we get more fuel in the cylinder in the same duration by increasing the pressure. This is a big deal with the common rail stuff. I've heard Josh McCormick over at Horse Torques, Power Driven Diesel, talk about going to higher and higher rail pressure to make more and more power. That's because with the same size injector, they can put more fuel in the chamber over the same amount of time by pushing on the backside of the fuel harder. And you can push on it as hard as you want until your components fail. So, like, common rails, cracked bodies. I don't think I've ever seen a cracked body for a 12 valve or a 24 valve. I could totally be wrong again, but we only run, I want to say, 6,000 to 6,600 PSI on a P700. We can raise that up to, I think, like some of the big pumps, 7,000, 7,200 stuff, but we're nowhere near the 30,000 PSI that you see in common rail systems. That's why we see, like, our injectors tend to have to be a lot bigger to make the same amount of horsepower than what it would take in a common rail. And we're really being real careful with that duration of it. How long is the injector open? And the other thing is, how long is the duration event versus where is the piston in the chamber? If we're spraying fuel into the chamber too late and trying to make cylinder pressure with the piston running its way down the bore, then we're not going to be making a lot of power, and it's going to be really dirty. Then you get this really slow burn. Diesel already inherently burns slow. So the more you screw this, is, one, it's really easy to screw it up, and two, the more you screw it up, the more fuel you got to put in to make the same amount of power, and you're just going to create a lot of heat and a lot of smoke because of that. Usually you got to put a lot of pressure in the system through RPM and boost pressure to get long duration events to work. So that's why you see, like, laser cut DVs, full cut DVs, really hard to tune, especially if you got CCs, could be nearly impossible to get to run clean down low because you get this long duration event. But the duration isn't necessarily long either. We talked about the capacity of the pump. 500 cc's takes a full rack travel, so it's 29 cc's a rack, meaning that the plunger is so say at full rack travel for us, 23, 29 cc's, whatever the pump builder sets it up to, or the Williams stuff sets for. we're injecting for that full duration, how long is that duration and crank angle in degrees? And that's been a topic that's also very hard to find a lot of stuff on. I've been looking into it a lot lately, probably the last half a year or so. But that duration event's really critical, and this tells you how much timing you got to put in the system if you even want to use it. Say 500 cc's takes 29 degrees at crank angle to put a 500 cc's a minute in at 3,000 RPMs. That means that we got to run, if we're doing an upstroke like a drag engine, we're going to run 30 degrees of timing because we minimum 35 degrees of timing because we have to get the fuel to heat up and mix, then go into flash, and from flash, more mixing and get to the main pressure event, and that all takes time with how fast pistons are going around. And how long does it take? We're going to look at a graph over time. If we looked at, what do they look like? They look like this. So let's say like this is our injection into the thing. Or let's just say this is cylinder pressure. So you see the piston coming up the compression stroke. Wherever we start injection, we'll see a loss in cylinder pressure for a moment. And that's the fuel cooling the air inside the compression event. And when even though the piston's coming up still, this is time, even though the piston is still coming up, the air is cooling at a rate that will kind of balance this out, or at least put a divot in it. It'll, it can be like that, it can be like this, but it won't continue on the same trajectory that we're seeing. So we'll be coming up in the start of injection, we'll do this, and what we'll see is it'll finally pull enough heat out of the compression event to start to light off. And when it lights off, it comes up, we hit peak cylinder pressure, and then we get this real long dragged out with diesel fuel. Gasoline is going to be much flatter drop. On average, diesel will burn for 60 degrees after it's injected, or for 60 degrees at crank angle since injection and since combustion started, should say. So start of injection, say it had at 20 degrees before top dead center. What we want to see, we want this to be 15 degrees after TDC. Let's say 0. And then we want it to maintain pressure from 15 degrees to 45 degrees. After that, the piston's running down the bore so fast that trying to chase it with cylinder pressure doesn't make torque. You got it? As simple as it is. Doesn't matter what engine it is, gasoline, methanol, diesel fuel, kerosene, B100, B20, whatever you want to name it. This principle is the same. The engines work just the same. Got a crank, got a connecting rod, got a piston, got a chamber. The only thing that's differentiating is the fuel type. So how we treat the fuel is different, but how we apply cylinder pressure is the same. Believe it or not, there's no differences on how we apply cylinder pressure to extract the highest work energy, BTUs, heat pressure, and turn it into work. There's a narrow window. So with this long burning fuel, what diesel does tend to do is, that's why we make a lot of torque, because we do push on the cylinder for a long time, but we don't really make a lot of horsepower with it because all of our peak energy needed to be here, yet a lot of our fuel is still burning out in this region. So that's why we see diesel fuel react to nitrous so well. So if we made the injector larger, what would happen here? Let's change colors, because we're going to a big injector. We left timing alone, left everything alone. We go to a big injector, what happens is this: start of injection, start of compression stroke, injection, and then I'll actually flatten this side out too because it burns crap. So we left everything alone. We went to a bigger injector. We just increased called the lag time, injector lag. Just increased the lag time a bunch. So now we have peak cylinder pressure is moved way out in crank degrees, way far down the deal. So we put a bigger injector in, and now it smokes more and makes the same power. We're putting more fuel in, but making the same power, if not less. We might pick up some. There's a lot of variables that go into it, but it's definitely going to be dirtier, and it's not going to pick up the amount of power that you want. When you change the injector, or you change the delivery valve, or you change anything that has to do with the injection system itself, typically the tune has to change up. In this case, we would need to start injection earlier. We need to start at, say that's a 10-degree sweep, then we need to go 30 degrees. And this stuff's all way over any of our ability to buy measuring devices for. You really got to use a dyno or your track time and what's coming out of the exhaust, like we talked about in the other video, to do it. Because like cylinder pressure devices to watch all this are really expensive. It's super awesome that Firepunk's doing stuff with that. I should say D&J, Firepunk doing really cool stuff with that. But you're not going to see your average hot rod diesel guy or over the tow daddy monitoring cylinder pressure. It's just not going to happen. So we got to do other ways to do it. But it just goes to show you how important having the right stuff is. I want to say it's called injector lag. Yeah, so you have start of injection, start of ignition, and then peak cylinder pressure, and the burn off. And the engine's rotating through this whole cycle. So the big thing is we just don't want to try to, if we get peak cylinder pressure, if it's chasing the piston down, the pressure does not expand at a rate that's comparable to piston speed, unless the piston speed gets really slow. The piston moves faster than you can imagine that it moves. And that pressure wave has to stay. The pressure wave itself, based on the condition in the chamber, because it's the pressure wave needs to stay subsonic. So even in diesel engines, a lot of people say that you detonate a diesel engine. Well, we're not detonating our flame front speed or flame burn. The subsonic burn, it's still, well, the burn rate and the pressure wave front speed is still below the speed of sound based on the conditions in the chamber. So how you do that in diesel is we just get the chamber really hot. The chamber is way hotter than what your EGT see, but you will see EGTs go up when you do this because you get there's all this excessive burn way late in crank angle, then the exhaust valve opens. Where does this go? It goes right to your EGT gauge. Whereas if you go to a smaller injector or add a timing to this thing, when operating at the RPM that the timing works appropriately at, a lot of the power stroke can actually be used to pull on the gas front itself. And when you pull on the gas front, instead of compress the gas front, we cool that down. And by the time the exhaust valve opens, we see a lower EGT on our EGT probe. That was actually probably a pretty important little piece right there. I think that'll help a lot of people understand tuning and what's happening inside the diesel engine itself. Don't forget to buy our super cool swag. Look at that shirt. We got plenty left, and we're going to be doing new hats pretty soon. But got to get the swag. All this stuff goes right into getting more cool stuff. So remember, this is Savage Fabrication, InstaSpool Performance. So the website is instaspoolperformance.bigcartel.com. You can find all of our stuff. Our YouTube is just where you're at right now, Bradley Carter. Don't forget to like, subscribe, ring the bell for notifications, put comments so we know what to talk about next. We got one comment that we did address in the previous video that we're putting up. And Instagram is Savage Fabrication, Bradley Carter, the only one on there that's modifying turbochargers with welds. So easy to find. There are a few of them, but we're the only ones weld on turbos. That's Savage Fab. So thank you for watching. Everybody have a good night. It's starting to get dark here. Thank you. Bye. Welcome back. Savage Fabrication, InstaSpool Performance, where we're going over all kinds and everything stuffs related diesel. That was a fantastic vocabulary to start this off.